Good day to you. Welcome to yet another session of electronics or embedded system. Today we are going to see introduction to CAN bus. So let us go through what are the attributes of CAN bus. CAN bus stands for Controller Area Network Communication and consists of two electrical wires called CAN low and CAN high. The information within each vehicle is being transmitted from and to ECUs. ECUs means electronic control units. In addition, CAN bus is built to handle robust performance within harsh environment. So mostly this CAN bus is used in automobiles. Automobiles is a harsh environment because of spark plug will create lot of noise which may interfere with any electronic control unit. That's why it's called harsh unit. Moreover, dust and heat will be present in the vehicle. So the whatever communication system or whatever electronic control unit one manufacturers has to undergo and perform nicely under all these conditions. It is basically a vehicle bus standard that allows microcontrollers or devices to communicate with each other. CAN bus is one of the protocols used in onboard diagnostic. Nowadays, the OBD2 is the mandatory in all newer cars and light trucks all around the globe. So you may see some similarity between this CAN bus and then RS485. Both are RS485 also only has two wires, and then the end of the bus will be terminated by around 120 ohm resistance. Similarly, CAN bus also exactly same like RS485, and it is also terminated by RS resistance 120 ohms at both ends. So this is the image of the OBD controller output. So you can insert a OBD scanner and then collect data from the engine through CAN bus. So this is one of the various models available for OBD2 scanner. Imagine that the car is like the human body and the nervous system in the human body is the controller area network in the car, which also enables the communication. That is, CAN bus is very similar to the nervous system which transmits information between various organs of our human body. Nodes or electronic control units are something like body parts like that are interconnected through a CAN bus communication. Information can easily be shared between parties. Depending on the type of the car, it can have up to 70 ECUs and each of them needs to be shared with other parts of the car. Type of a car means expensive car like Audi, BMW and all may have 70 ECUs, and the smaller cars like Hyundai i10 and all may have less number of ECUs. Some of the examples are, for instance, audio system, airbags, engine control unit, door control unit and so on are examples of ECUs. The CAN bus enables the ECUs to communicate to each other. The CAN bus uses two wires for communication, CAN low and CAN high. ISO 118982 describes the physical layer of the CAN bus and ISO 118981 describes the data link layer. The physical layer represents types of cables, node requirements, electrical signal levels, cable impedance, baud rate, cable length and termination, etc. Cable length should be 40 meters. If the transmit rate is 1 bits per second, or it can even go up to 500 meters if it is 125 kilobits per second. Longer the transmission distance, slower the bit rate, but in automobiles 40 meters is more than good enough to communicate between two ECUs. The CAN bus has to be terminated using a 120 ohm CAN bus resistor at the end of each bus. CAN nodes have to be connected through two-wire bus with baud rate up to 1 megabits if it is CAN 2 or 5 megabits per CAN FD. Basically, CAN bus is not master-slave communication. So any device can communicate to any other device. So all the devices listen for the communication, they receive the data. So one device will transmit and all other devices will receive the data. And while decoding data, then it decides whether the information is meant for that particular ECU or not. So the information that whose the information belong to is embedded in the data itself. There is a particular field where this information is saved, that identifier is saved. So that identifier is decoded to understand whether that particular message is for that ECU or not. This is where the communication happens. So always all the devices listen in this whole. There is no master, there is no slave. So anyone can communicate any message and anyone can receive any message. This is the protocol followed in the CAN bus. CAN bus follows layered architecture. This is an example of CAN FD, the latest one they are announced by Bosch. Data link layer, it consists of logical link control, MAC, medium access control layer. The LLC corresponds to the nodes, controller host interface and concerned with message filtering, overload notification and recovery management. Its scope is to decide which messages received by the MAC sublayer are actually to be accepted, to provide services for data transfer and for remote data request, to provide messages to the MAC sublayer for transmission, to provide means for recovery management and overload notifications. There is much freedom in defining object handling. MAC sublayer of the data layer, data link layer. The MAC sublayer is responsible for message framing, arbitration, acknowledgement, error detection and signaling. It is supervised by a management entity called Fault Confinement, which is a self-checking mechanism for distinguishing short disturbances from permanent failures. Within the MAC sublayer, it is decided whether the bus is free for starting a new transmission or whether a reception is just starting. The MAC sublayer represents the kernel of the CAN FD protocol. It is in the nature of the MAC sublayer that there is no freedom for modifications. Physical layer handles bits and defines how signals are actually transmitted and therefore deals with the description of a bit timing, bit encoding, bit synchronization. Within this specification, the electrical driver receiver characteristics of the physical layer are not defined so as to allow transmission medium and signal level implementation to be optimized for the application. So this block diagram is of a MCP2518FD, the CAN controller from microchip. It is communicates to the host ECU through SPI. So on the right side you can see top 4 pins, CS, SCK, SDA, SDO, they are all SPI communication pins. And then there are INT, interrupt 0, interrupt 1. They are all to communicate with once again with the microcontroller for start initiating the communication, receiving of information, something like that. And the bottom 2 pins, RX scan and TX scan, is actually do the communication with the CAN bus. This is a block diagram how the CAN controller is connected to the microcontroller. There are 2 power supplies. One supply gives the 3.3 volt for the CAN controller and 5 volt DC is given to the CAN transceiver. There is another IC which need to be connected to the CAN controller, which will directly connect to the CAN bus. So general description of the CAN transceiver. The ATA6562/3 is a high-speed CAN transceiver that provides an interface between a controller area network protocol controller and the physical 2-layer CAN bus. The transceiver is designed for high speed up to 5 Mbps. That is the latest standard. That is CAN bus FD. CAN application in the automotive industry providing different transmit and receive capability. A CAN protocol controller. It offers improved electromagnetic compatibility and ESG performance as well as features such as ideal passive behavior to the CAN bus when the supply voltage is off, direct interfacing to the microcontrollers with the supply voltage from 3 volt to 3 volt to 5 volt. So we have come to the end of this small presentation about CAN bus. Thank you for watching.